For the prop beam shown, determine the following by double integration method and by superposition method. EI is constant. The vertical deflection at A, the moment reaction at C, and the angle of rotation at B. In the superposition method, we will use the tool I developed for beams with one end perfectly restrained. So if you can recall, EI theta equals moment at the wall, length over degree plus 1, while EI delta is equal to moment at the walls, L square over degree plus 2. So first by double integration method. This is indeterminate to the first degree, and we will select RA as our unknown, extra unknown. So we cut x, so EIY double prime equals RA times x minus 24 times x minus 3 times x minus 3 over 2, or minus 12x minus 3 square. So that's the moment equation up to this section here. So integrating once, EIY prime equals RAX square over 2 minus 4 quantity x minus 3 square plus C sub 1. So there is slope at A, but there's no deflection at A when x is 0, so there's no C sub 2. Integrating again, EIY equals RAX cube over 6 minus quantity x minus 3 to the 4th plus C sub 1x. So there's no C sub 2. There's no need to evaluate it because when x is 0, y is 0. So boundary conditions at the far end, when x is 9, the slope of the tangent at the fixed end is horizontal. So that means y prime is 0 when x is 9. So let's evaluate C sub 1. 0 equals RA 9 square over 2 minus 4 times quantity 9 minus 3, so 6 cube plus C sub 1. So formulating the first equation, 40.5 RA plus C sub 1 equals 4 times 6 cube or 864. Call that equation 1. So again, EI y double prime equals RA times x at this section here. Then minus 24 times quantity x minus 3, x minus 3 over 2, so that's why minus 12 x minus 3 square. Integrating once, RAX square over 2 minus 4 times quantity x minus 3 cube plus C sub 1. Then integrating again, AIY equals RAX cube over 6 minus quantity x minus 3 to the 4th plus C sub 1x. And when x is 9, because this is fixed, so when x is 9, the slope here is 0, the deflection is also 0. So let's have the slope 0 first. Y prime is 0 when x is 9 to formulate the first equation into this equation. So 0 equals RA 9 square over 2 minus 4 6 cube plus C sub 1. So 40.5 RA plus C sub 1 equals 864. Then when x is 9, y is 0 into this equation. 0 equals RA 9 cube over 6 minus 9 minus 3 or 6 to the 4th plus C sub 1 times 9. So formulating the second equation, 121.5 RA plus 9 C sub 1 equals 1296. So you may multiply equation 1 by 9, then subtract it from equation 2 to solve for RA. So solving these two equations simultaneously, R sub A equals 80 over 3 or 26.667 kilonewtons in decimal. Then into equation 1, so C sub 1 would be negative 216 after we substitute 80 over 3 in equation 1. You'll get C sub 1 equals negative 216, the slope at A. So we can now compute the moment reaction at C. Take note that EIY double prime is moment, so if we substitute it here when x is 9, then we can evaluate the moment at C. So EIY double prime is moment at C when x is 9, so 80 over 3 times 9 minus 12 times 9 minus 3 or 6 square. So moment at C is equal to negative 192 kilonewton meter. Then the angle of rotation at P. When x is 3, into this equation, 80 over 3 times 3 square over 2, this is 0, then plus negative C sub 1, which is negative 216. So theta B can now also be computed, negative 96 over EI. Now for the superposition method, I'll use the formula developed in superposition method when one end is fixed. So this is the unknown RA, so I apply it so that it will deflect upward, and at A we'll call that delta A due to the reaction delta R. Then using the formula EI delta R, and this is due to the load, effect of the load. So this portion is straight because there's no loading here, only this part will bend, and the slope of the tangent at the end of the load is theta L, which remains the same here because this portion is straight. So therefore, this is denoted delta 2, and because this is 3 meters, the opposite side of a right triangle, theta L, is very small, remember from principle on deflections, that therefore this is 3 times theta L, 3 times theta L, or tangent theta L equals opposite over 3, so that's why this is 3 theta L. Delta due to the loading therefore is the sum of delta 2 and 3 theta L. Let's just make it positive. This is treated positive also, so that when we combine, we can equate the two. So for the loading EI, delta R equals moment at the wall, which is 9 RA, L square, which is 9 square because it's 9 over degree plus 2. So remember the formula. So delta R, the moment at the wall due to RA is RA times 9. So that's why we have 9 RA. The length is 9 also, so L square divided by degree of the moment diagram due to RA would be triangular, so that's why it's first degree plus 2, and 2 is a constant in the formula. So simplifying, EI delta R equals 243 RA. Now for the loading, the moment at the wall, EI delta 2, the moment at the wall is 24 times 6 because that's 6 times 3. So EI delta 2 equals moment at the wall 432 L square because that's 6 square over degree of the moment diagram due to this rectangular loading or uniform loading is 2 plus 2. Remember second degree spandrel. So simplifying, EI delta 2 equals 388. Then that's kilonewton meter cube. Then for theta L, EI theta L equals moment to the wall for 32 times L over degree plus 1. So remember the formula. Moment of the wall, so 42 is 24 times 6 times 3. So EI theta L equals 864. Therefore, EI delta L, the entire deflection due to the load, is 3888 plus 3 times 864. So EI theta L equals 6480. Equating the two, EI theta R must be equal to EI theta L. There's no net deflection at A. So EI delta R equals EI delta L canceling out EI because it is constant. So 243 RA equals 6480. So R sub A equals 80 over 3 kilonewtons, which verifies our answer from double integration. Now, having found RA, we apply statics this time to solve for M sub C. Summation moment C equals 0. So this is the positive direction of MC. Just assume positive always. So RA times 9 minus MC minus 24 times 6 times 3 equals 0. So R sub A times 9 minus M sub C minus 24 times 6 times 3 equals 0. So from there we can solve M sub C equals negative 192 kilonewton meter. For the slope at B, we have to apply a pair of equal forces downward, which is RA, and upward RA. Then the downward RA and upward RA will constitute a couple, which is RA times 3, as shown in this figure here. So this is 6 meters. The 80 kilonewton meter couple is RA 80 over 3 times 80 over 3 times 3. So that's why 80 kilonewton meter. There is still an upward force here at B of RA, which is 80 over 3. Remember from statics that you can add a pair of equal forces at any point without changing the effect of the original system. That's the principle. And I did it here because due to the load, there is value of theta L which is positive because this is inclined up. So due to the effect of this couple and upward force, it will deflect like that, like this. So the slope is negative. So the net slope at B therefore is the slope due to the effect of this couple and upward force at B, then plus theta due to the load. So that's the slope at B. So for the theta R, so moment at the wall, EI, negative EI theta due to this reaction, 80 over 3. The moment at the wall is 80 over 3 times 6, so that's why 160. Length 6 over degree, again, is first degree plus 1. So EI theta R is negative 480. Then EI theta due to this moment is moment at the wall, which is still 80 because that's moment. Length 6 over degree 0 plus 1 because the moment diagram for couple is just rectangular, so it is horizontal 0 degree. EI theta M therefore is also negative 480. Finally, the slope at B is this negative 80 plus this negative 80 plus theta L, which is 864 at B. So negative 480 minus 480 plus 864 due to the load, which is positive. So the net slope at B is negative 96 over EI, which is the same as this. That's it for this problem.